So, good afternoon. We will start the discussion for week 8 of the NPTEL course Power System Engineering. So, the previous week we studied two different methods for the load flow studies of the radial distribution system. So, if you remember briefly, we studied two algorithms for load flow of distribution systems. The first one was the backward forward sweep method. Backward forward sweep. And here we calculated both the voltage magnitude and the voltage angle at each bus. But then, since in the studies of the distribution system, we don't really care about the voltage angle, like that is not a very important quantity. So for the method 2, what we do, we uh, omit this voltage angle and we derive the expression containing only voltage magnitude. So here we calculate only the voltage magnitude at each bus using that P loss formula as we had seen in the last class. And now in this week, we will see how to study the voltage stability of a distribution system. So, voltage stability, first of all, what do we mean by it? So, we know that at each bus in the distribution system, the voltage magnitude should be within a predefined range. The voltage magnitude should be limited between a range V minimum to maximum for the smooth operation. Like if the voltage falls below the minimum threshold value or it goes above the maximum threshold value, then it will hamper our system and sometimes it will lead to also partial or complete interruption of the power supply leading to blackout that we see. So this minimum value generally we consider V minimum as zero point 0.9 or 0.95 per unit, and the maximum is generally taken between 1.1 to 1.05 per unit. So at all states of the power system, at each and every bus, the voltage should lie within this range. So what are the factors that will affect the voltage of the system? So the factors affecting voltage stability are: firstly, it will depend upon the loading of the system, like whether the system is heavily loaded or lightly loaded. So if it is heavily loaded, means the voltage will fall or drop. So there are chances of under voltage problems to occur when the system is heavily loaded. On the other hand, if the system is lightly loaded, then it may lead to over voltage problems in the system. That it is likely that voltage may go above 1.1 per unit. So this may lead to over voltage problems in lightly loaded condition. So the voltage stability. So we define certain indices to measure this voltage stability, and by looking at this index we can say what is the strength of the system now, whether it is weak or it is strong. So that we'll see how to calculate this index or indexes. Then it will also depend upon the power transfer levels of the system. Also, the voltage is closely related to reactive power or Q. We know that, right? So whenever the voltage tends to decrease below, let's say, zero point 0.9 per unit, or if it increases above 1.1 per unit, then what we do, we have to take some corrective actions, right? We have to take certain corrective actions to bring the voltage back to the safe operating level, right? And generally, these corrective actions are always taken with the help of reactive power. So whether depending upon the voltage of the system, we may inject or absorb. Uh, can you please mute yourself, Pooja? Or I am muting you. So generally, wherever we inject or absorb the system, so accordingly, the voltage of the system is corrected. So let's say if you don't have enough reactive power available in the system, then obviously you cannot activate it. Then you cannot. This we generally call as Q reserves. So if these Q reserves are not there, then you cannot activate the reactive power required, and hence you cannot correct the voltage violations. So generally the sources of Q, let's say the sources of reactive power. So earlier it was the synchronous machines. Then we may have a shunt reactors or capacitors connected at the substation level. Then there may be your OLTC transformers. Then there may be your FACTS devices also. So these were some of the sources of reactive power. So utilizing these sources of Q, we used to manage the voltage of the system. Now, when we have a renewable rich grid, so that means synchronous machines are not present, right? Or are less in number, are quite less in number. That implies that you do not have enough reactive power support in the system because they were the major sources. You do not have enough reactive power support to the system. So now it is mandated that the renewables also need to support the grid by providing this reactive power, by providing the required reactive power at their point of connection or their PCC. So generally it is required that they should maintain a constant power factor at the PCC. So what will happen now is we know that there is a capability curve, right? So what this capability curve gives, it gives the relation between the amount of P and Q, amount of P and Q that can be generated in any machine. So generally, if the x-axis is the amount of P generated and Q is on the y-axis, so here positive and negative means injection or absorption. That's why Q can have positive or negative signs, right? So it is generally a circular curve. So what happens is, let's say this is point O, this is point A. So at point O, you can see the amount of P generated is 0, whereas the amount of Q generated is the maximum. And at point A, the amount of P generated is maximum, whereas the amount of Q generated is 0. So you can see as you move from point A to point O, the active power generation capability, it is decreasing, whereas the reactive power that can be generated, that is increasing. Which means that, let's say, initially the generator is operating at a point P, right? So it is at, let's say, point P, or P will confuse you. So let's say it is R, and let this be S. So let this be P1, P2, this be Q1, this be Q2, right? So let's say initially you are at point R, or the machine is operating at the point R, which means that the active power produced is P1 and the reactive power produced is Q1. Now let's say there is a need for reactive power in the system of Q2. So for generating Q2 amount of reactive power, the P, or active power, has to reduce from P1 to P2, right? And wherever such a condition happens, where to support this grid, to provide this reactive power Q2, If the generator has to reduce its active power generation, then they get payment from the grid for supporting, right? Because the payment to the generator is always for the active power. So if to support the grid, the generator has to reduce its active power. That means the generator expects the payment for it because it is for the grid, and whereas generators, they will be profit seeking entities, so they will need some incentives to support the grid. So hence, whenever to supply additional reactive power to the system, if the generator has to reduce its active power, then it receives payment from the grid for the amount of active power reduced by the generator. So this was for the synchronous machines. So for synchronous machines, for production of Q, so it does not require any additional equipment or raw material. So hence the cost of producing Q in a conventional synchronous machine, only Q, is negligible. So earlier the payment was only when there was reduction for active power. But now when the renewable reach this your solar and they are coming into picture, so they require inverters, or that we say as batteries, for producing the reactive power. And these equipments, they have certain cost, right? They have their own cost. So now the cost of Q is not negligible for the renewables. So if we are mandating or taking reactive power support from these renewables, we also need to pay for the we also need to pay for Q generated or observed. So this is establishing the need for reactive power pricing today, right? In the today's scenario, where we have a mix of this asynchronous and this renewables. Okay, so let us see that how we will calculate this voltage stability index. So if you remember, while computing the method 2 of the load flow, so we came across of a uh, equation for this voltage, which was biquadratic, right? Was a power 4. So that equation, if I rewrite, it was something like V2 to the power 4. So that is a magnitude plus 2 V2 R1 plus Q2 X1 minus 0.5 V1 square multiplied by V2 square plus R1 square plus X1 square into P2 square plus Q2 square, right? So here basically this we were considering, let's say, a branch JJ whose receiving end is sending end is M1 and receiving end is M2. So V2 is the receiving end, right? And R1, X1, they are the resistance and reactance of this line 1. So for this example, your line is 1, receiving end is node 2, and sending end is node 1. So considering these values, we have written this equation. Now, if we do some modification here or adjustment here, so what we'll do, we'll take the 2, multiply it in the inside the bracket, and take negative side common. So what we will get here is, so this will be positive and half will cancel out, and this will be negative, and 2 times P2R1 minus 2 times Q2X1. Rest all are same. R1 square plus X1 square, P2 square plus Q2 square. So if we write it in the generalized form, so it is Vm2, that is receiving end node voltage, to the power 4 minus sending end node Vm1 square minus 2 Pm2 is the node at this M2 node at the resistance of the line Jj, minus 2 Qm2 reactance Jj, line Jj, then Vm2 square plus resistance of line Jj, reactance, this is Pm2 plus Qm2 square. So now let us take Vm2 square as x. So what will happen? This equation, it will reduce to x square minus, before that, let us define two quantities B and C. So just a second. Yes. So let me write this BJJ. We define another constant here. So that is this bracket Vm1 square minus 2 Pm2 Rjj minus 2 Qm2 Xjj, and let Cjj be the constant part. So Rjj square plus Xjj square, Pm2 square plus Qm2 square, and additionally let me take Vm2 square as x. X will be confusing. Let us take it as t. So now what will happen, this equation 1, we can rewrite it as, so it will be t square, because Vm2 to the power 4 minus Bjj times t, minus, let me just I am neglecting the node numbers, so Bjj I am writing as B times t, right? So this one, so this is B, this is t, this is t square plus c, plus c equals to 0. Now we have a quadratic equation, and we know So it will have its roots as plus minus of, so it is no, it is minus b. So minus of minus b plus minus square root of b square minus 4. A is 1 here and c is c. We have taken it here, right? Divided by 2a, where a is 1. Basically, we get that. But now we know that this t we have taken it as v square, right? Vm2 square. So it is b plus minus b square minus 4c. Let me just write here cjj bjj jj. So divided by 2. So what will be vm2? So this will be plus minus square root of bj plus minus square root of bjj square minus 4cjj divided by 2. So what we got? We got 4 possible solutions for VM2. So if you remember from these 4 solutions, we had seen in the previous week that only one solution was feasible. So let us see why out of these 4 solutions, how we discard 3 and we consider only one. What is the logic behind that? So let us first observe the value of B. So if you see BJJ was Vm1 square minus 2 Vm2 Rjj minus 2 Qm2 Xjj. Now, if you consider for a practical distribution system, so Vm1 is the sending end, right, at the head. So this value will be always 1 or near about 1, right, 1.0. And if you that is in per unit, and if you consider the per unit values of this rjj, it is small, it is in the order of 10 to the power minus 3 or 4 sometimes. Similarly, pm2 is also small, so their product, so product of two small quantities will be further small, right? So it will be negligible, we can say. Similarly, for these two also, we can say their product is negligible. So it turns out that if you see, so if you subtract, like this is a large quantity and we are subtracting two very small quantities, so that means this will result that bjj will be always positive. Similarly, if we see cjj, so it was rjj square plus xjj square into pm2 square plus qm2 square. So this is all our square terms, that means they are positive. That means they are positive. Plus we had seen that pm2 and rjj, similarly qm2 xjj, they were small, so their squares will be further smaller, right? So yeah, just a second. Yeah, so these are positive because they are square and they are further small. So cjj is also small or negligible compared to BJJ. So now if you see the term under the square root BJJ square minus 4CJJ, so BJJ square minus 4CJJ. So we had seen that BJJ square is greater than 4CJJ. So that will, yeah, since this is the condition, so this will be nearly equal to BJJ square, right? So what will happen is those two roots, what will happen? V will be plus minus root of B plus minus, it was B square minus 4C, which is nearly equal to BJJ square divided by 2. So this turns out to be plus minus BJJ by 2, because, or let me just write the four roots once again. So first root is square root of BJJ plus minus BJJ square minus 4CJJ divided by 2 whole square root. Similarly, second one is BJJ minus BJJ square minus 4CJJ divided by 2 whole square root. The third one is minus BJJ plus BJJ square minus 4CJJ divided by 2 whole square root. Similarly, minus BJJ minus BJJ square minus 4CJJ by 2 whole to the power half. Right. So from this you can see the voltage magnitude, it cannot be negative, right? So straightly this 3 and 4 cannot be the feasible solution. Now from these two equations, if you see, so one is BJJ plus this term by 2. Similarly, other is minus term. So from this two, we can say that this will also be not feasible, because your BJJ, we have seen it is greater than 4 times CJJ, right? So from all this, what we finally get is, so this is the only feasible solution for V. Now let us derive the condition for feasibility. So for that, we need that this square root bjj square minus 4cjj, that should be a real number, right? So we want that this term, it should be positive. If it is negative, then it will give rise to conjugate, right? That iota term. Then again, that is not feasible. We need real solutions, real. That for that, the condition is this should be greater than equal to 0. If it is 0, then we get repeated solution, and if it is greater than 0, then we'll get real solution. So for satisfying that, so we write bjj square minus 4cjj has to be positive or non-negative. So let us expand that then. bjj was vm1 square minus 2pm2 rjj minus 2qm2 xjj square. So that is greater than equal to 4 times cjj was rjj square plus xjj square into pm2 square plus qm2 square. So let us expand this both LHS and RHS. So let us consider that this is A, so this is, let's say, A, and minus, if we take common, then this will result in 2pm2 rjj plus 2qm2 xjj whole square. So let this be B. So if I expand it, it will be A square, that is vm1 to the power 4 plus 2pm2 rjj plus 2qm2 xjj square, then minus 2ab. So A is vm1 square and B is 2pm2 rjj plus 2qm2 xjj. So, and that will be greater than equal to this rjj plus xjj square into pm2 square plus qm2 square. Now let us again multiply this. So that will give us vm1 to the power 4 plus, again I open this quadratic, so it will be 4pm2 square rjj square plus 4qm2 square xjj square plus 8pm2 8pm2 qm2 rjj xjj, then multiplying this one, so that will be minus 4 vm1 square pm2 rjj minus 4 vm1 square qm2 xjj and that will be greater than equal to 4 times rjj square pm2 square plus 4 rjj square qm2 square plus 4 xjj square pm2 square plus 4 times xjj square qm2 square. Right. Now certain terms they will cancel out. So let us see this one and this one. Similarly, this one and this one. So now this will reduce to Vm1 to the power 4 minus 4 times. So we collect the coefficients with V1. So these are constant. Here we have Vm1 square, Vm1 square. So minus 4 Vm1 square Pm2 rjj plus Qm2 xjj, and if we bring these two terms to this side and this 8 times will this will basically be again a minus b whole square, right? So if I take as -4 as common here, so this and this, so they will be, let me write first p terms, so it will be pm2 xjj minus qm2 rjj whole square. So this has to be greater than equal to 0. So this is your stability index, this term stability index for node M2. This is defined as the stability index. So what we do, we calculate the stability index as M2 for all M2 equal to 2 to number of buses, and then we calculate the minimum for all this stability index into number of buses, then we get the minimum stability index value of the system that we see. So normally if I plot stability index versus the system loading, so this will be the total reactive power and this will be the reactive power. So with the increase in loading of the system, the stability index will fall. Right. So in this direction, loading is increasing. And lower the stability index, greater are chances of voltage collapse, or greater is the sensitivity of the voltage of that bus, right? So now we will see another method, approximate method for calculating the stability index. So let me insert one slide. So another approximate method. Approximate method for voltage stability calculation. So let's say we have a series circuit like this with a line connected between them of resistance R and reactance X. Sending end voltage be Vs, receiving end voltage be Vr, and I be the current flowing through this. So if we draw the phasor diagram here, so what it will be like? So we start from the receiving end, right? Receiving end is our reference that we say always. So let's say this is your Vr, and let I is lagging behind Vr by the angle theta. So now what will be IR, since R has no phase difference, right? So it will be parallel to I. So its phasor is parallel to I, but magnitude is IR. And now Ix, it will be perpendicular because this J operator, it will rotate it by 90 degree. So this is your Ix, and Vs is your Vr plus IR plus JIX. So their phasor sum will give me Vs, and this angle we call the delta, right? And this is this triangle, if you see, this is IR, this is Ix. So their phasor sum will be Iz, where your Z is R plus Jx, right? Now let us observe the geometry of this figure. So let me draw or extend this line here, this line here, and we drop a perpendicular from this point. So if you see, this angle was theta, right? So this is also theta. Now let me also drop a perpendicular from here to here. So this is again a right angle triangle here. So again we get this angle as theta, right? So this angle is again 90 degree minus theta. So let me name these points. So let this point be O. Let this be A. Sorry, this be just a second. Yes. This point is O, this point be A, this point be B, here this one, and this be C. So this be C dash, and this point be B dash. So from here, I can say what is AB. So AB dash is so this is IR. That means AB is IR cos theta, right? Similarly, BC is same as B dash C dash, and that is the part of triangle IX. That is IX cos of 90 minus theta, which is same as IX sin theta. So if we see this OC, so OC will be is the part of this bigger triangle which has VS in its hypotenuse, right? So that will be VS cos delta, and also OC is OA plus AB plus BC, and that will be OA is your VR, AB is IR cos theta, and BC is IX sin theta. So if we consider delta as small, and then if we compute this OC, then equate basically, so we get Vs delta is small means cos delta is nearly equal to 1. So this will be Vs equal to Vr plus IR cos theta plus Ix sin theta, right? So this is, if we calculate the voltage drop, that is Vs minus Vr, that is I times R cos theta plus X sin theta. Now let us calculate the maximum voltage drop that can occur. So for that, what we need to do, we need to differentiate it and equate it to 0, right? So we have to differentiate the expression for voltage drop. So d times voltage drop by d theta. So voltage drop was I times R cos theta plus X sin theta. So that will be minus IR sin theta plus Ix cos theta equal to 0. So from here what you will get as R sin theta equals to X cos theta, or tan theta is equal to X by R. So the maximum theta max you get as tan inverse X by R, and maximum power factor that you can get is cos of tan inverse X by R, that is your power factor. So we can say that the voltage drop is maximum when power factor is equal to the impedance angle, right? And now, lastly, we'll see for a radial system how to calculate this voltage drop. So let's say we have let this load be drawing IC, IB, and IA. This be VA, B, and C. So let the branch currents be I1, I2, and I3. So what will be I1? So I1 will be IA plus IB plus IC. Or let me write backward, then it will be clear to you. First I3 will be IC, right? And what about I2? I2 will be I3 plus IB, and I3 is IC, so IB plus IC. Similarly, I1 is IA plus I2, and I2 is IB plus IC. So now let us write voltage at point A. So that will be V0 minus I1 Z1, right? The drop in this line I1 Z1. So that I can write as V0 minus I1 is IA plus IB plus IC. Z1 I can write as R1 times JX1. And what about VB? VB is VA minus I2 Z2. So that is, and VA minus I2 is IB plus IC R2 plus JX2. And VC is VB minus I3 Z3. So that is VB minus IC times R3 plus JX3. So like this you can calculate the voltage at the point VA, VB and VC. So if you for the distribution system, the X is smaller than the R, right? So if we neglect the terms which are with uh, which are multiplied with X basically, then what will be this total voltage drop? So that will be IA times R1 plus IB times R1 plus R2 plus IC times R1 plus R2 plus R3. So neglecting the reactance, that is your total voltage drop. So we'll use it while solving the problems. So let us go to the assignment question. So the first is, if the load in a distribution network increases, then what happens? Voltage profile improves, voltage profile becomes poor, system losses decreases or increases system losses. So what do you think? What will be this answer here? Whenever load will increase, what will happen? Would you like to attempt which is the correct answer here? This voltage profile we saw, right? So whenever loading increases, then your stability index decreases, and whenever index is decreasing means the voltage profile is poor, right? So from this, 2 is correct. And what about losses? Load will increase means, yes. If you want, can you tell which option is correct? A, B, C, D, which one? What will happen to the losses if the load is increasing? Okay, you say B, means according to you, loss will increase. Yeah, right. Yes, you're correct. Thank you for the answer. So loss will also increase. So the correct option is option B. Now the second question. A node with low voltage stability index is more susceptible to voltage collapse, less susceptible, always unstable, or voltage stability cannot be ascertained from voltage stability index value. Which one is the correct option, do you think? Yeah, so this we had discussed, right? That's why we were calculating the minimum voltage stability index for all M2. And so this will give us the SI minimum. So that node for which the stability index is minimum, that is more susceptible or vulnerable to voltage collapse. So option A is correct. Now this is the question here. So right, ring distributor system is given and it is being fed by a 280 volt supply. This one, right, Vs is equal to 280 volt. The resistance of each section is zero point 0.2 ohm per 100 meters. Okay, and the loads are tapped off as shown. So at each point, this B, C, D, and D, different loads are present, and the current drawn is given. So arrange the voltages at these points in ascending order, and then length of the each section is given. So let us calculate this. So there is First of all, AB, BC, AB length is 200 meters. That implies its resistance will be zero point 0.2 into 200. So that will be 40, right? Then ohms. Similarly, what about BC? BC is 300 meters. So our BC will be 60 ohms. What about CD? Is also 300 meters. So our CD is 60 ohms. Then DE is 400 meter. So our DE is 80 ohm. Then EA, it is 200 meter. So our EA is 40 ohms. Right. So let us write the KVL in this loop here. So let this current be X. So like this, let us consider. So if I write the KVL here, so what it will be? It will be X times RAB, which is 40, right? So 40 times this plus BC is 60. And what will be the current? So this is X is incoming, 40 is tapped off at point B. That means BC will have X minus 40 or 40 minus X? X minus 40, right? The remaining. Similarly, then CD is having again 60. So another 10 will go. So X minus 50. Then next is DE. So DE is 80. So it is X minus again 30 will go. So 80. Then E is 40. X minus 100. That is equal to 0. So how much I'll get here? 40, 60, 100. This is 200. So 280x minus 60 into 90 minus 80 into 80 minus 4000 is 0. So 280, how much I can divide here? I think 4. No. So 280x equals to, this is 5400 plus 6400 plus 4000. So x will be 8, I think 10, 15 by 280. So that will come out to be, so x will be 56.4285 amperes, right? Now once we have calculated the current X, now we have to calculate the voltages, right? So let me insert a slide. So from VA is 280, so we'll calculate next VB. So VB will be VA minus X times RAB. So VA is 280, and that is 56 point something. We got 4 3. RAB was 40, right? Yes, 40. So we'll get it as 280 minus 56.43 into 40. No, something. Sorry. So actually here it is 0.2 ohm for 100 meters. That means this resistance I have computed wrong. So this will be just zero point 0.4. This is 0.6. This is 0.6. Then, sorry, this is correct. This is correct. Yeah. And RDE is zero point 0.8, and this is zero point 0.4. Right. So 0.4, 0.6, 0.6, 0.8, 0.4. So I think this will be common here. That's why it is not making difference. So this is 0.4. 0.6, 0.6, 0.8 and zero point 0.4, zero point 0.8, zero point 0.4. So I think this will also scale down by just instead of 280, it will be 2.8, right? Two places the decimal will just shift, and here it will be just so this will be 40, and this will be zero point 0.8 into 80, so 8 into, yeah, so this will be 64, and this will be just 30. So did I miss anything? 1 2 3 4, and here also 24, right? So This is minus 24, this is minus 30, this is minus 64, and this is minus 40. So that will come out as 158. This will be 2.8. So we get x as 158 divided by 2.8. This will be same because ratio, yeah. So this is same. So AB was 0.4, and here we have two conductors, right? Go path and return path. So two conductors means resistance will be also for two wires, so two times. So that will give me as 280 minus 86.43 into 0.42, just zero point 0.4. So that is 257.428. Now what about VC? VC is VB minus RBC, and what is the current in BC? It was X minus 40, right? So VB is 257.43 minus, so this is 16.43, right, times RBC. RBC is 0.6. So I get this as 257.43. Yeah, so this is 247.572. Now what will be VD? VD is VC minus, I think it was 50, right? Yeah, CD is 50. So X minus 50 RCD, and VC is 247.57 minus, so this will be 6.43, and what is RCD? RCD is 0.6. So that will give me minus 6.43 to 0.6. So 243.714 volt. Similarly, VE will be VD minus RDE, and that will be, previously it was X minus 50, so now it is X minus 80. X minus 80, so 243.71 minus, this will be minus, so 56.43 minus 80, that will give us minus 23.57 times, what is RD? It is 0.8. So that will give us 243.71 plus 23.57 into 0.8, so 262.566 volt. So ascending order, that means lowest is VD, then it is VC, then VB, then VE. Right. So which one? So the greatest is VE, E, B, C, D. So option D. Okay. Now let's see the next question. So again, a rain distribution system is given and the loads are given, and there is an interconnector CE. So this is at 380 volt. The resistance are 100-meter length of AB are 0.1, 0.2 and 0.2. Determine the current flowing. So let's say this current is X, this current is Y, and this current is Z. So here this be I. So the total input current will be the total output current. And what is the total output current here? It is 20 plus 30 plus 40 plus 10, right? That comes out to be 100 amperes. So let us write the KVL in loop BCE. Yeah, so this was 10, 40, so 100, and we were writing the KVL in BCEFB. So that will give us with, so X times, so its resistance is 0.2 ohms, X times 0.2 plus what will be the current here, Z times, so the ring interconnector is also 0.2, so 0.2 and its length is 250. Then so 0.2 per 100 meter means this will be 2.5, right? So that will be equals to, now up to this I have dropped for E, we have calculated now through this part, right? So BF is Y. So again 0.2 and length is 1.5 plus, that will be Y minus 40, 0.2 into 1.5. So this will be Y minus 40. So from here, if I calculate, so X is 0.2, Y will be, so 1.5 times 0.2 and 2 times, so minus 0.6 Y, and Z is 0.2 into 2.5, that will be 0.5 Z, and the constant will be 40 into 0.2 into 15, 1.5. That gives minus 12. That is your equation 1. Now let us write the KVL in C, D, E, C. That is in the upper half, right? So for CD, what will be the current here? So X minus Z minus 20. So X minus Z minus 20 into 0.2 into 2 plus, what will be the current here? X minus Z minus 50. So X minus Z minus 50 times 0.2 into 2. So that will be equal to Z times 0.2 to 2.5. So that will give us, basically this is 2 times 2 into 0.2, that gives us 0.8. So 0.8x, and same, this will be also 0.8, and another 5 will come here, so 1.3 Z, no, minus 1.3 Z. And what about the constant? Constant will be positive only, so 0.2 to 2 into 17, that gives 28. This is your equation 2. Now last, another KCL we need to write just. So at KCL at node C, if we write, or at node B, then x plus y is 300. Sorry, x plus y is 100. So x plus y is the total current that is input, that is 100. So that gives us equation 3. Now let's say solve 1, 2 and 3. So solving that, you will get x as 53.8 0.056 ampere, Y as 46.944 ampere, and Z as 11.11 ampere. So it acts the current through the interconnector, right? And what is it? The current to the interconnector is Z, right? So that is equal to Z, that is 11.11 ampere. So option B. Now let us see the next question. So two distribution systems, they are represented by their sending and receiving end nodes. All lines have same impedance. Loads are same. Loads at all buses are same. Both systems have 1 point per unit voltage. So which system has better voltage profile? So are these connections same? No, from here that is different from here. So let us first draw this system. So system 1. So 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. Okay, this is just one main feeder with 10 nodes, right? And what about system 2? It has 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 3 to 7, 7 to 8, 4 to 9, 9 to 10. So their topology are different, but the line parameters and the load values, these are same. Which will have better voltage profile, system 1 or system 2? Both will have same voltage profile, or it cannot be a certain. What do you think it will be the answer? Just give it a try. Which one do you think? Option C, both will have same voltage profile. So no, because we'll see how they'll be having different, because they are not, interconnections are not same. So let's say I want to calculate this voltage at ninth bus. So let be ninth for system 1. So that will be V1 minus, we had seen that equation if you remember. So the voltage drop at C. So for that, what will happen? It will be IC times. So basically this part, right? This part is your voltage drop from O to C. This is voltage drop for O to B, and this is O to A. So what is happening? It will be the current that is drawn here, and then the resistance of all its head feeders, right? So if I similarly write it here, so voltage drop So that will be, let the current drawn here be I9. So I9 into resistance of all this line, right? R1, 2, 2, 3, 3, 4 up to, or let me write it, R4, 5, 5, 6, 6, 7, 7, 8, till you reach the ninth node, right? So that will be the voltage drop here. But similarly, if I try to calculate the voltage drop for system 2, so what will be the voltage drop here? That will be I9. They will draw the same current because we have seen that they are same load are connected, right? It is given loads are same and the line resistance are also same. So here you will get R12, 2, 3, 3, 4 plus R4, 9. So you see the voltage drop is less here, right? For the same node 9 for both the systems. So the voltage drop are less. So less voltage drop means better voltage profile. Similarly for node 7, 8, 10. So if you see for here, basically for the voltage at this end, that will be lower than voltage here, right? Are you getting this? So if I see this group, so basically V system 1, this will be less than V system 2, and we have seen that minimum voltage means voltage collapse chances are more. So that means system 2 is more having better voltage profile. So that's why system 2 is asking. So I hope this is clear. Now next question. So two distribution systems, again sending and receiving are given. Line have same impedance. Loads are connected. Voltage is 1 per unit. Okay. So now you can see the connection is same, right? For this 1, 2, 2, 3, 3, 4, 4, 5. So the topology is same, but the load are different, right? And for each node, the system 1 is having greater load at each node compared to, no, for the head feeders, and in the system 2 basically here these are having greater loads, and here these 1 to 3 are having greater. But what about the sum? So let us calculate. So to system 1, system 1, system 2, so total active power here it will be 320, 270, 210, 165, 130. So that gives 5, 10, 16, 17, 19, 3, 4, 6, 8, 10. So I think this is nearly 1095 kilowatt. What about reactive power? that is 280, 235, 180, 125, 90. So 10, 10, 20 plus 11, 31. 3, 5, 7, 8, 9, 9, 10 kVAR. For system 2, it's 305, 260, 240, 180, 145. Again 10, so 10, 18, 22, 23, right? 5, 7, 9, 10, 11. Kilowatt. And what about reactor? It is 270, 225, 195, 135, 100. So 15, so 10, 20, 22, 2, 4, 6, 8, 9. So when we calculate the total load, so system 2 is having greater total load for both P and Q, right? And if you remember this plot, that stability index versus loading, so it was both PL and QL. So as this TPL or TQL increases, the stability index decreases, which means voltage instability. So since system 2 has greater loading condition, so it will be having poor voltage profile. So system 1 will have better voltage profile than 2. So which is having, so system 1 is having better stability index. This is clear, right? Okay, now let's move on. So a radial distribution network is given. 4 buses are there, and the line reactance, resistance, and active and reactive load are given. So consider the substation voltage as 1. Find the voltage magnitude of bus 4 after first iteration. So this was the previous week assignment only. So here R is given in ohms, means you need to convert it into per unit. So what will be the Z base? Is kV square by MVA base, right? kVB base square by MVA base. So 11. So that gives 121 ohms. So what will be from that? We need to calculate the per unit one. So I will draw the system. And let's say the line number is, this is line 1, line 2, line 3. So 1, 2, 3. So Z1 is your R1 plus JX1 divided by 121 per unit. Z2 is R2 plus JX2 divided by 121 per unit. And similarly Z3. Okay. Similarly, you need to convert the loads also. So for load, you need to divide by what is 1 MVA. That means 1000 kVA. So this is in kilowatt, means kVA is, so it has said that the loads are connected to the two bus, right? So PL2, QL2, PL3, QL3, PL4, QL4. So all these will be divided by 1000, right? So that you'll get the per unit values. So up to here only we have converted the actual to per unit conversion. Okay, I hope this was clear. Now for method 2, what you used to do, first we'll assume loss are 0, right? So P loss, Q loss for the first line is 0. For first line, second line, third line, first line, second line, third line in the 0th iteration is 0. Now for line 1, so receiving end is 1, sorry, sending end is 1, receiving end is 2. So if you remember the formula for A and D, that was AJJ, means line 1, P2R1 plus Q2X1 minus 0.5 V1 square. Similarly, D1 will be A1 square minus R1 square plus X1 square into P2 square plus Q2 square whole square root. So from here you can calculate A1, D1, and then from P2 was the total electrical equivalent of load at node 2. So that will be for P2, all this will be there. So PL2, PL3, PL4 plus loss in P loss line 2, 0th iteration plus P loss in line 3, the 0th iteration. Similarly, Q2 is QL2 plus QL3 plus QL4 plus P loss, Q loss second and third iteration. So this value of P2 and Q2 you need to substitute here and in this formula also. R1 X1 you had already calculated here, right? This one. Then V1 for line 1, this is 1.0, right? So that one also you know. Then you can calculate A and B 1. From that you can calculate V2 as D1 minus A1 square root. So if you do all this, you will get V2 as 0.9818 per unit. Now let let's write for line 2. So J is 2. So 1 is 2, 2 is 3. So A2 is P3 R2 plus Q3 X2 minus 0.5 V2 square. And D2 is A2 square minus R2 square plus X2 square P3 square plus Q3 square square root. And here P3 is PL3 plus PL4 plus PLOS line 3, right? So this one at bus 3, so P3, P4 plus loss in line 3. Similarly, Q3 is QL3 plus QL4 plus loss in line 3. So again, if you substitute and then uh, calculate A2 D2, from that he can calculate V3 as D2 minus A2 square root. So from that you will get it as 0.9690 per unit. Now similarly you can write for the last one, right? So J is 3, so M1 is 3, M2 is 4. So similarly E3 D3 is P4 R3 plus Q4 X3 minus 0.5 V3 square. This is V3 square plus R3 square plus X3 square P3 square plus Q3 square whole square root. And here P4 is just PL4 and Q4 is just QL4. So from here we can calculate V4 as D3 minus A3 square root. So that will give it as 0.9633 per unit. So from here 0.989696. So 0.96 to 0.98. So it is asking at bus 4. Bus 4 we are getting as 0.963. So option D. So answer is D. Now, so is it the same? Yes. So 250, 2.42, 3.2, 800. Yeah, the data is same as the previous. So after first iteration, we have calculated the voltages already. So now we just need to calculate the voltage stability index. So if you see voltage stability index at bus number 3, right? So we had derived it. So this was right. So it was so voltage stability index at bus 3 is equal to, so this was the system. So this is M2, this is M1, this is JJ. 1, 2, 3. So JJ is 2, M1 is 2, M2 is 3. So here we get as V2 to the power 4 minus 4 PA3 x2 minus Q3 R2 square minus 4 P3 R2. See here it was VM1. So in our question M1 is 2, right? So I wrote V2 to the power 4 minus 4 V2 square P2 P3 R2 Q3 x2 minus 4 P3 x2 minus Q3 R2 square, right? So minus 4 P3 R2 plus Q3 x2 into V2 square. So we have calculated already with the value of V2 in the previous question. So if you put those values here, you will get it as 0.8816 per unit. So that is option B. Okay, these two questions we will solve in next class. Our time is over now. So if you have any doubts, you can ask. Otherwise, we'll close the session and we'll discuss the last two questions in the next class. Any doubt? Otherwise, we'll close it. Thank you, Chef, for joining. So we'll meet in the next week for the discussion. Right now, I'm closing the session. Thank you for joining.